Okay, so we're going to be discussing experiment 23A, which concerns amide synthesis. In this case, we're looking at the synthesis of acetanilide. Okay, so the reaction that we're looking at is the reaction between aniline and acetic anhydride. So in this case, we have a nucleophilic nitrogen-centered nucleophile, an electrophilic carbon-centered nucleophile. And in this reaction, aniline will attack acetic anhydride. We will generate the following tetrahedral intermediate. And the intermediate will collapse, and we would lose an equivalent. We will lose an equivalent of acetate in this case. This acetylation reaction works best under mildly basic conditions. And in this case, that is often why we add in this experiment a small amount of sodium acetate to facilitate this deprotonation step to get our final product. So we've generated acetanilide via this one-step and very robust acetylation reaction. One thing that I would like you to note for your percent yield calculations is we use an excess of acetic anhydride, both because acetic anhydride slowly hydrolyzes over time during storage and to minimize losses due to side reactions with water. So we've seen acetanilide before, and if you actually have your old Chem 112 reports, you would be able to find your tabulated physical properties for acetanilide in your old report tables. Okay, so when we run our reaction, so we have our reaction mixture. So let's talk a little bit about the aniline for a moment. So when we take our crude sort of reactant aniline, we often like to clean up our crude reactant. And the way that we're going to do that in this case, is via treatment with charcoal. So charcoal is useful for removing colored impurities, and it's a useful method to help clean up and remove particularly metal or very polar impurities. So in this case, we're going to transfer our aniline to the activated charcoal, and then we'll transfer from there into our reaction flask. We're going to be doing the semi-micro scale prep, which is scaled by a 5x scale. The reason why I'm bringing up that the aniline is purified over charcoal is that you may lose a small amount of aniline during this purification step, but purifying your aniline over activated charcoal drastically increases the efficiency of this reaction and drastically improves the purity of your final product. So in our reaction flask, we're going to add our aniline. Going to add the acetic anhydride and our sodium acetate. This reaction occurs quite readily over room temperature conditions. we will isolate and we will observe a solid that we will isolate via filtration. In the Hirsch funnel, once we have isolated our solid, we will then wash our solid with diethyl ether and water. From there, we will be able to obtain and weigh out the mass of purified acetanilide product. This is a very robust reaction, a very fast reaction. And I found a pretty nice video of a reasonably large scale prep that closely matches the procedure performed, and I've tabulated all the physical property and mass data that you would need from our run through of this experiment. So once we've purified our acetanilide, we're going to collect a few things. First, we're going to collect the melting point. And again, just like before, you're going to look at the percent error compared to the literature value, and you're going to talk about the melting point range, right? If the range is less than 1 degree Celsius, that's an indication of purity. The next thing that we're going to collect in this case is an IR spectra. The IR spectra will be collected in nu-joule. What I would note is even if you have a literature spectra and KBR, you won't see anything significantly different. The only thing about nu-joule is because nu-joule is a hydrocarbon, you will see the CH sp3 signals pretty broadly in nu-joule. Any questions so far? Any questions so far on the mechanism? Any questions so far on what we're doing in this lab? This is a very fun reaction to run because it's dump and stir. It's very straightforward. You can see the product precipitating out as you watch. The other thing that we're going to collect, and because the video is relatively short, I've included not only the proton NMR, but the carbon NMR. And I found proton and carbon NMR on a 400 megahertz device, 400 megahertz NMR instrument. So you'll be able to, for this lab in particular, explicitly assign your multiplets, singlets, doublets, and triplets. So you'll be able to more effectively note the splitting pattern, and I've included the integrations. So for example, if you look at your proton NMR spectra, you'll be able to note the multiplets, the singlets, doublets, and triplets, if applicable. One thing to note is I have the proton and carbon NMR in deuterated DMSO and deuterated chloroform, just to make it easier to compare to the literature. Outside of the melting point, IR, proton NMR, and carbon NMR, we're also going to be looking at a series of solubility tests. These solubility tests are covered in Chapter 9, and we're also going to be looking at a chemical test for the amide equivalent. So in terms of solubility tests, the way this is going to work, there is a flow chart in Chapter 9. Let me pause for a moment just so that way I can pull up the flow chart for your reference. Give me 1 second. I paused the recording just because I closed the tab when I was lecturing, so you didn't see my email going off every few seconds. Give me one moment just to pull up the exact page in Vital Source or on the textbook, so that way we can talk about that together. So if you go to chapter 9 of your lab manual, reporting. So in your lab manual, there'll be a solubility flow chart. So this provides you a method to differentiate compounds based on their solubility in different solvents. So initially you're going to check for water solubility. And since we're dealing with an amide in this case, because we're dealing with an amide, we would expect the amide, looking at this chart, would we expect the amide to be water soluble or insoluble, looking at this chart? So we find our amide in the chart, and we notice that the amides are noted as being water soluble, while insoluble in sodium hydroxide and generally insoluble in dilute hydrochloric acid. Does that make sense to everyone so far, how to read through this table?
Wait, can you show me where the amide is? Where it says amide?
The amide, it's in section 2 on the third branch from the top. It's of the form RCONH2.
Okay. Thank you.
One important thing about amides compared to amines or carboxylic acids is that they're litmus neutral. So generally you wouldn't see a change when you dissolve the amide in water. If you test the pH of that solution, you would expect to see a neutral solution. The other thing to note is that if we compare amides to acid salts, hydrochlorides, amino acids, amides are generally ether soluble. So by observing the solubility in different solvent systems, you'll be able to in turn determine and identify whether or not you have an amide versus an amine. Now, one thing to note about this branching chart is that each test is done sequentially as you move from left to right on the chart. Oh, that's not an amide. So VI talks about amines. And one of the differentiating factors between an amine and an amide so let me talk about that a little bit then. So when you look at the water solubility, most of the amides are water soluble. So at this first juncture, you'd see solubility in water. If you treat your same amide sample and you try to dissolve it in sodium hydroxide, dilute hydrochloric acid, and concentrated sulfuric acid or concentrated phosphoric acid, in this case, if you try to dissolve your amide in sort of sodium hydroxide or hydrochloric acid, you would expect to observe a slight decrease in solubility in these slightly acidic and slightly basic solutions. The main thing that's useful about the test by trying to dissolve it in sodium hydroxide or hydrochloric acid is that it allows you to differentiate between an amine versus an amide, because the amine would be characteristically insoluble in slightly basic solutions such as 5% sodium hydroxide, but soluble in slightly acidic solution. The one differentiating factor, if you compare an amine versus an amide, is that if you try to dissolve an amide in 5% hydrochloric acid, for example, So if you try to dissolve an amide in 5% hydrochloric acid, the amide would be insoluble while the amine would be soluble. And that's what that juncture is trying to convey. Does that answer your question? Though typically the moment you see water solubility, that's a signpost that you're likely dealing with an amide rather than an amine. Now, these solubility tests are great, but they're not actually the principal signpost test that we'll be using in this case. So in this case, we're going to use a textbook classification test. And this is a common test that also works on esters. So let me find it for you. So we're going to be dealing with the hydroxamate test for amides on page 591. So this is a very interesting test because it deals with a carbonyl substitution reaction to convert our amide or our ester for that matter into a hydroxamate. The one benefit of generating this hydroxamate is that it coordinates iron to generate a colored complex. So in the first step, we're treating our amide with hydroxylamine hydrochloride. We heat this mixture to promote the substitution reaction, carbonyl substitution, to make our generated hydroxamate. And then by treating with iron trichloride, if we see a red-violet color, that implies that we have started out with an appropriate amide. So the red-violet color after reaction with hydroxylamine followed by iron trichloride is a positive test for an amide. Does that make sense? And that's because this substitution occurs specifically when you have an amide or an ester, and this product will only be colored if it's coordinating iron with this specific structural pattern. Any questions so far on the chemical tests that we're using for this lab? Let's keep going now and let's talk about the one other test that we're doing. We're not doing sodium fusion. That test is a bit jumpy and requires dealing with sodium at high temperatures. So instead, we'll be using the alternative test, which is the soda ash test. And I'm pulling that up right now. The reason why I'm showing you in the lab manual is so that way you can help find the pages. So we're going to be doing the Sodalime test. Does everyone see this test? It's on page 580. And the Sodalime test is different than the fusion test. So what the Sodalime test is detecting is the presence of ammonia generated from your amide. So nitrogen-containing compounds in the sodium fusion test and the soda-lime test, for that matter, will evolve ammonia. And as a result, by detecting the presence of ammonia generated over the course of this reaction, we can in turn determine whether or not our compound had nitrogen and whether or not we have an amide present. So generally, if we observe a change in our litmus paper or brilliant yellow indicator paper, that provides us an evidence that as we heat this mixture containing our product compound, soda lime, and magnesium oxide, that implies that our original compound contained nitrogen, and that ammonia in turn results in a change in the color of our litmus paper. So if our litmus paper changes color, that's a sign that our Ammonia was generated and our original compound contained nitrogen. So with these tests together, we're confirming the presence of an amide, confirming the presence of a nitrogen functionality, and from solubility, that provides additional evidence that we have an amide present. Does everyone understand the chemical tests that we'll be working through in the laboratory today? So in terms of the chemical tests and in terms of the solubility tests, so first things first, we're going to be taking our product and we'll be subjecting it to the solubility flowchart. We'll add that in a moment. We're just doing a recap for now. So in the first case, we'll look at the water solubility. So amides are typically soluble in water, while amines are insoluble. You're then going to be looking at the solubility in sodium hydroxide, 5%, and then the solubility in 5% hydrochloric acid. So amines are soluble in 5% hydrochloric acid, while your amides are not. Finally, as one last test, we'll be looking at the solubility in sulfuric and phosphoric acid. And in both cases, we would expect to see a positive result, or solubility in concentrated sulfuric and solubility in concentrated phosphoric acid. So that's our first part. That's the solubility tests. Does everyone understand the solubility tests? Does everyone understand the logic behind the solubility tests? So for the next part, we're going to be doing the chemical tests. So the hydroxamate test. So we're going to take our amide, in this case acetanilide. Oops, wrong way. And then what we're going to do is we're going to treat our acetanilide with the hydroxylamine hydrochloride salt. They will react. We'll generate this tetrahedral intermediate. And then that tetrahedral intermediate will collapse and will generate a hydroxamate. The reason why this is important and the reason why this is diagnostic is that when we treat this mixture with a solution of iron 3 chloride, we see coordination of our iron to generate a characteristic red-violet colored solution. And this color change after reaction with hydroxylamine and treatment with iron 3 chloride gives us a positive chemical test for an amide functional group. Does everyone understand the hydroxamate test? Okay. The next test we'll be doing is the Sodalime test, otherwise known as the soda ash test. In this case, we're going to take our product and we're going to add to it manganese dioxide and soda lime. and then we are going to heat this mixture. Now, what's really important to consider is that when we heat this mixture, we are going to have a piece of litmus paper. And what's going to happen is as the reaction proceeds, we're going to be generating ammonia. So as a result, what you will see is that the litmus paper over time in this reaction will start to change color. And this observable color change indicates that ammonia was generated. Ergo, our product contains nitrogen. We're not doing the sodium fusion test, as that test gives the same general interpretation, but is far more operationally dangerous. Does everyone understand the role of the Sodalime test? It's essentially an exhaustive oxidation of our product and degradation of our product. And as a result, ammonia gas is liberated from our product if it contains nitrogen, and that in turn will change the color of our litmus paper during heating. Any questions on the Sodalime test? Okay, so for our final test, we're also going to deal with the ignition test. And the ignition test, just like before, will confirm the presence of an aromatic. So just like before, we'll have our spatula. We take a little bit of solid on our spatula and we'll heat it. And if we have an aromatic ring, we would expect to see a dark, sooty flame. That in turn tells us we have an aromatic functionality. So you'll be given a table in the experiment page containing the masses of reactants and products. You'll be able to watch a recording of the procedure being performed. All of the spectra are already posted to Canvas, and you'll see the results of each of the chemical tests tabulated as well in the lab page. Does that make sense to everyone so far? Is everyone comfortable with this experiment? Does this experiment make sense to everyone so far? So that's a comprehensive overview of experiment 23. So you're responsible for analyzing the melting point, IR, NMR data, as well as interpreting the chemical tests. Any other questions that I can address on this lab? Yeah, they're going to be added and opened up momentarily.
Professor, I have a question.
Yes, please go ahead.
Do we have to include in the procedures like how to perform the chemical test?
Yep, so you should include a procedure for each of the chemical tests using the procedures referenced in the lab manual, just like I showed you from the lab manual.
Okay, thank you.
Any other questions I can address on this lab? So, yes. You should include in your reagents and hazards table the major reagents used for each test. In terms of the spectra that you would need for your final report, you just want the IR and NMR of the product and the reactant aniline. That's all I want for this lab. So you don't have to worry about a giant spectra list, just the reactant aniline, the product acetanilide, and any experimental spectra that I give you on Canvas. The reagents for the chemical test, so the procedure itself tells you which solubility tests will be performed. So in this case, for this lab in particular, we're looking at the solubility in water, 5% sodium hydroxide, 5% hydrochloric acid, concentrated sulfuric acid, and concentrated phosphoric acid. The exact procedure for the solubility test is given in the lab manual, but you're just mixing a small amount of the solid with about 1 milliliter of the solution and observing whether you see a homogeneous or heterogeneous solution after mixing. You don't have to talk about the preparation. Yes, you're also looking at the ether solubility, and that's a separate solubility test from the sequential group. And as we discussed in the flow chart, when we think about ether solubility and we think about whether or not amides are ether soluble, we generally observe that amides, looking back at our solubility chart table, let me pull that up just so that way we can be on the same page for this. We see in general that amides are ether soluble. The other thing I want you to note is that after we note water solubility, if we go back, we're also going to be testing the pH, and we know that amides in general are litmus neutral in solution. Does that answer your question? Does that clarify? Sure. And you want to make sure for your procedure that you include and you follow the rinsing step for the lab manual. Let me just correct that. So our product doesn't have to be purified through any other external trituration. We're just rinsing our obtained solid with water. If you wanted to partially dry your solid, you can use a small volume of cold ether, but water is sufficient for the purification. Does that address your question? Yes, to answer the question in the chat, amides are insoluble in 5% sodium hydroxide and 5% hydrochloric acid, but they're soluble in sulfuric and phosphoric acid. That is correct. Amines, by comparison, are soluble in hydrochloric acid. And so based on the solubility in hydrochloric acid, it allows you to determine whether you have an amine or an amide. So if we don't have any other questions, we'll pause this recording. I want to show you the